Hello, everyone, and welcome to the webinar titled AI for Safety Critical Systems. My name is Sanila Mary, and I am an application engineer at CES, the authorized reseller of MathWorks in the Middle East. Artificial intelligence is becoming more present in our daily lives. And what once seemed like the realm of fiction is now becoming an everyday convenience, enhancing our experiences in the ways that were once unimaginable. As AI continues to evolve, its applications are expanding into more critical domains where the stakes are significantly higher. Today, we will discuss the exciting topic of incorporating AI models into safety critical systems. Here's the agenda of the webinar. We will begin with an introduction to AI-enabled system. Next, we will explore how MATLAB and Simulink support the development of AI-driven systems. These tools provide a powerful environment for designing, simulating, and implementing AI models, enabling rapid prototyping and integration into embedded systems. However, as the innovation comes with the complexity, we will discuss the unique challenges in verifying and validating the AI-enabled systems. In the next section, I'll provide an overview of AI certification in airborne systems, touching on current frameworks, emerging guidelines, and the implications for safety assurance. To bring these concepts to life, we will take you through a case study focused on certifying a DALD level runway sign classifier. This practical example will illustrate how AI models can be developed and assessed for compliance within the aviation standards like DO 178C. From there, we will look at what it takes to move from design assurance level, aka DAL D to DAL C certification. As the design assurance level increases, so do the complexity and rigor of the requirements. We will outline what needs to change and the path forward for more critical applications. We will then summarize the key takeaways from our discussion, focusing on the essential considerations, current progresses, and the future outlook of AI certification in safety critical systems. Finally, we will wrap up by talking about how you can begin your transformation journey. With the right tools, guidance, and industry collaboration, organizations can confidently navigate the path to AI integration and certification. As I mentioned earlier, AI is rapidly transforming our daily lives, from personal assistants on our smartphones to chatbots on customer service websites. As AI technology advances, it is increasingly being used in industries such as healthcare, aerospace, and automotive, where it has the potential to revolutionize the way we work and live. However, as AI use rise in production environments, there is a growing need to explain, verify, and validate the model behavior, especially in safety critical situations. The safety critical industries such as aerospace, automotive, and healthcare require AI models to be highly reliable and trustworthy because incorrect or biased decision can have severe consequences. For example, in aerospace, incorrect AI decisions can lead to accidents or fatalities, compromising the safety of passengers and crew. Whereas in automotive industry, a faulty AI-enabled system can lead to accidents or injuries, endangering the lives of drivers, passengers, and the pedestrians. If you consider healthcare, incorrect diagnosis or treatment plans made by AI system can lead to patient harm or even death, hence jeopardizing the health and well-being of the individuals. Therefore, it is crucial to ensure the accuracy, reliability, and trustworthiness of AI-enabled systems in these industries through proper verification and validation techniques that meets respective industry standards. Last but not least, a certified AI system is not just a technical achievement, it's a business asset that can open doors to new opportunities, and it can strengthen your brand, and it can also help you win more contracts faster. Let's take a look at some of the key market trends in the aerospace industry, particularly around certified systems, software, and hardware. First, we will consider the civil aerospace. In civil aerospace, we are seeing rapid innovation, new applications like urban air mobility, UAV certifications. These are becoming major areas of focus. And there is also a strong momentum around sustainability with the technologies like green aviation gaining traction. More recently, the importance of cybersecurity and even AI certification have grown significantly as these systems become more intelligent and connected. In the space sector, a lot of private companies are now voluntarily following standards like DO 178C to ensure high quality even then they are not formally required to do so. This shift reflects increasing pressure to meet the expectation of space agencies like NASA or ESA, European Space Agency. New entrants New entrants are also aggressively pursuing certified projects, intensifying the competitive landscape. If you consider defense programs, we are seeing an interesting trend. About 70% of the defense projects are now targeting civil certification equivalents. This is largely due to the growing complexity of the modern systems, particularly system of systems that involve a high degree of autonomy and intelligence.
Webinar AI focus.
These projects are pushing the boundaries of traditional
Okay.
certification processes. And here we have addressed some of the common customer needs and the pain points. It includes the certification process is sometimes too expensive and complex, and the defects are frequently discovered late and during the integration or the testing phases. Documentation requirements are tedious and time consuming. And finally, qualifying tools for certification adds another layer of difficulty. And how can MathWorks helps here? First, we support a model-based design workflow which can streamline the development and verification. We encourage the use of verification and validation tools early in the process, helping to catch the issues sooner. We also offer tools We also offer tools for automated artifact generation, which reduces the documentation burden significantly. And finally, our DO qualification kit and IEC certification kit for ISO 26262, it provides the evidence and guidance needed for standards compliance. Next is AI-driven system design with MATLAB and Simulink. Let's get into the specifics of AI-driven system design. It involves four main stages: data preparation, algorithms and modeling, simulation and test, and finally the deployment into the field. It's important to note that this workflow is not linear. In many cases, it is iterative, especially when testing uncovers the improvements that need to be made. Drilling down to each of these sections, it reveals a mini workflows, and this will need to be performed. Okay, each of these have their own challenges. Okay, and first step in this workflow is actually the data preparation. So the data can come from multiple sensors or databases. Sometimes it is structured or unstructured. Sometimes it spans the time, but with the different time intervals. It can be noisy. It represents different domains and so forth. One goal of the data preparation is assessing these various sources of data. Not all data is critical, and some has more highly predictive value than others. And some of the events are extremely rare and it may not be included in a given data set, but still you need to consider that for modeling. So engineers with domain expertise are best suited to determine the answers to these kind of questions. With the toolboxes for all major engineering domains such as signal, image, control, statistics, and more, MATLAB brings that power to your engineers' fingertips. If you consider data labeling, MATLAB provides tool to enable an iterative and exploratory approach to building large and well-labeled data sets for many different applications. For example, this image shows our app for labeling images for semantic segmentation, in which the regions of an image are classified and then that classification is automatically applied. And with our signal labeling app, and it's a similar process that can be applied to a wide range of signal data. In this example, we are labeling whale sounds. Both these apps also provide ways to automate the labeling process and save many hours of time. Next, we provide like a facility for synthesis for creating synthetic data. Okay, so this can be vitally important where you are trying to build an AI algorithm that successfully handles extremely rare events. Let's move on to the second step in the workflow that may be the most that may get the most attention: AI-based algorithms and models. Of course, it's important to have direct access to many algorithms used for classification and prediction, from regression to deep networks to clustering. And there are a variety of pre-built models developed by the broader community that you want to use, often as a starting point or for comparison purposes. While the algorithms and pre-built models are a good start, it's not enough. Examples are the way engineers learn how to use algorithms and find the best approach for their specific problem, particularly reference examples. So here in MathWorks, we provide reference examples which are built for every specific engineering applications. We provide hundreds of examples for building AI models in a wide range of domain. Is that the like that's not the end? We also provide apps for modeling. For deep learning in particular, we ship pre-built apps that can help you automate the training step and provide visualization for understanding and editing deep neural networks. And there is another app, it's called classification learner. So these kind of apps and the regression learner automate those steps as well. And then comes the experiment manager app. It enables you to create deep learning experiments to train networks under various initial conditions and compare the results. And finally, AI models have to be incorporated into a larger systems to be useful. Okay, so if you consider the example of automated driving, there is a lot of algorithm work around perception systems, like designing perception algorithms that can collect data from multiple sensors and fuse those data into an understanding of what surrounds the vehicle. But for those algorithms to be effective, they have to integrate with the algorithms for localization, path planning, agent and environment management, and controls, all working together to make sure that the vehicle accelerates, decelerates, brakes, and steers perfectly in any situations. This can be accomplished with an overall system simulation that handles not just the perception algorithm, but the entire vehicle itself. The vehicle and the other vehicles and the actors such as pedestrians, bicyclists, etc. And the simulation should be performed across multiple driving scenarios in multiple weather and environmental conditions. You can handle all this through simulation based in Simulink. And this is how it all works. Okay, here is a small video. Engineers can combine the sensor fusion, control logic, vehicle dynamics, and visualization components with their AI models for simulating the scenarios in which they will operate. Here, this example shows how a vehicle and lane detector works in a self-driving car. Next is about the deployment. We have unique code generation framework that allows models to be developed in MATLAB and Simulink, and you can deploy it anywhere without having to rewrite the original model. Automatic code generation eliminates the coding errors and is an enormous value driver for any organization adopting this. The power and flexibility of our code generation and deployment framework is unmatched. So deploying an AI model is not the end of our system design workflow. Organizations are also understanding that deploying models into systems is not an end state and it must be maintained continuously once they are in operation. In recent times, model DevOps or the model ops is a process that the organizations are adopting to manage the life cycle of models. In essence, model DevOps is a combination of software development, IT, and model development practices. Here is a familiar representation of model DevOps. Across all the stages, it's not one, but a combination of different software pieces running on the edge or in the cloud, coming together to build a complete solution. So I have spoken about how MATLAB and Simulink is used in the design and deployment of AI models. But for the model develops, MATLAB and Simulink integrates with all major platforms that are used across each of these stages. MATLAB plus Model DevOps enables cross-team collaboration to align the goal of engineering, computer science, data science, and IT for the model lifecycle management. And why MATLAB and Simulink for artificial intelligence? There are numerous benefits to building AI-driven products and services with MATLAB and Simulink. Your engineers can leverage their expertise without becoming programmers. Using domain-specific tools, they can design powerful algorithms that incorporate years of experience and can handle rare events. They can use modeling and simulation to tackle integration challenges and reduce risk. And the end result can be deployed and managed wherever it needs to be without recoding. Next is the challenges in verification and validation of AI-enabled systems. So here is some of the challenges. Okay, so if I have to name a few, it includes data management, traceability, robustness, requirements, and much more. So it's just a representative sample of some of the challenges that may arise from having AI components in our system. If we consider some examples, first thing is AI systems, especially deep learning models, can behave differently due to the randomness in training, floating point precision, and sensitivity to small input changes. This unpredictability makes it hard to verify the behavior under all conditions. Another challenge is the lack of explainability or the black box nature. Many AI models, example neural networks, act like a black box. We don't fully understand how they make decisions. This makes it difficult to trace why a certain output has produced, which is critical for debugging, certification, and safety audits. Another challenge is about the data dependency. AI system performance depends heavily on the quality, diversity, and representativeness of the training data. Verifying that the data covers all relevant cases, especially the corner cases, is difficult. Bias or gaps in the data can lead to unsafe or unfair decisions. Okay, now let's see how can we address some of these challenges. Okay, the deep experience in safety critical certification enable us to drive new standards for AI. Okay, so we know that some of you may be working in the regulated industries that have these kind of standards that you may use our certification kits to ensure that the system you make meet appropriate standards. So these standards govern the safety critical systems for airborne software, road vehicles, and sometimes it's for the healthcare industry. The problem is that some of the verification methods they prescribe can be performed or don't necessarily make sense for machine learning or AI related systems. So this IEC certification kit ISO 262, it's mainly for the automotive, and DO 178C and DO 254 is applicable for aerospace related. And we are happy to inform that MathWorks is participating in the standards committees with EuroK and SAE to define new certification standards that are appropriate for artificial intelligence. We know how important our current safety critical certification solutions are for our customers, and we are working to build new standards needed for artificial intelligence and then to provide you with the tools needed to certify your systems that include AI. In healthcare industry also there is a similar standards preparations happening. FDA has released its first AI or ML based software as a medical device action plan, which outlines the regulatory framework for AI enabled medical devices. Next is AI cert. We'll have a look at the AI certification in airborne systems before we move to our case study. Let's Okay, why certifiable AI in aviation? Okay, so the technology has advanced in leaps and bounds, reducing the cockpit workloads for the pilots and making flying safer. But you can see an image there in my slide. Not so long ago, it used to be the case that you would find four people in the cockpit of an aircraft. This image is the cockpit of a Boeing 707, which doesn't operate commercially anymore. But back then, apart from the pilot and co-pilot, it was common to have a flight engineer and a navigation engineer on board. As the technology evolved, many tasks have been overtaken by the software such that nowadays you can mainly find a pilot and a co-pilot on board of the commercial aircraft. So there are numerous benefits that the incorporation of AI could bring in the future, including single pilot operation, predictive maintenance applications, voice recognition system in the cockpit, runway object detection, visual collision avoidance, autonomous flights, and many more. Now, we cannot simply design an AI component and use it in the airborne systems. There are rules or better set standards to be followed. The aircraft standard related to software design is given by DO 178C. Now, let's see what is DO 178C. It's a standard for software consideration in airborne systems and equipment certification. This software standard outlines the software engineering processes, activities, and tasks necessary to ensure that airborne software is reliable, safe, and it can perform its intended functions. It defines five software levels that are based on the potential impact of software error on the aircraft safety operations. These are referred to as design assurance levels or DAL, or I will be using the term DALs. Okay. So compliance to DO 178C is mandatory for software used in civil aviation applications and in many countries. The latest version of DO 178C was released in 2011 December, and it includes updates to the previous revision like a DO 178B to reflect the advancements in the software technology and development process. But this will not It turns out that several DO 178C objectives cannot be directly applied to the software with the machine learning component, and this creates a problem. How are we then going to use machine learning into aviation software and certify it against DO 178C? How can we build trust in new verification methods for machine learning? The potential is huge, but the gaps and shortcomings need to be addressed. For that matter, industry and regulators are working tirelessly and making significant progress for machine learning certification in aerospace. EASA, the European Union Aviation Safety Agency, has published two iterations of their AI roadmap and worked together with various companies to produce seminal work for design assurance of neural networks and the use of formal methods for learning assurance. FAA, although it hasn't published as much collateral, also stays at the forefront of these developments. Another significant entity in AI certification for aerospace is EuroK WG114 or SAEG 34 Joint International Committee. It is expected to release the new process standard soon, which will set the standard for development and certification or approval of aeronautical safety related products implementing AI. And the standard is named as ARP 6983. They have already published in April 2021 an aerospace information report, Artificial Intelligence in Aeronautical Systems. Uh, and MathWorks is playing an active role in this group also. Now let's see how big is the gap between machine learning and traditional software development. We know that for rule-based software, we have well-established definitions and methods to show compliance with objectives. We have DO178C, and so we can look at some code. We can look at some code, and we are able to trace it back all the way to our requirements, produce the coverage matrices, and understand or explain its behavior. However, it's not the case when machine learning is incorporated. In fact, there are 15 out of 71 DO178C objectives that are incompatible with ML components, that's the machine learning components. We know this from the working group efforts on the statement of concerns document published in 2021. And so we would like to be able to answer what each of these concepts could mean. So essentially, there are known gaps, but as we do not have any new standard yet, we wanted to see how far we can go with the current standards. Can we develop a workflow to address the certification of ML components using the current standards? And the answer is that for low criticality applications, yes, we can, if certain assumptions about the ML development workflow are applied. In fact, I firmly believe that focusing on understanding the boundaries of the current standard, it will help you and your organization to be ahead of the curve for whenever the new standards are released. So, can we certify machine learning now? I have already given you some hint about that. Now let's focus on how we will do it. Okay, this work is based on, the case study or the further slides that we are going to showcase. It's actually based on a joint research between a Technical University of Munich, MathWorks, and NASA. It was mainly carried out by a person named Konstantin. He is a developer at MathWorks and research associate at TUM. The intent is to take an incremental certification approach, leveraging existing standards, starting with a low criticality design assurance level for machine learning workflow. This allows us to reduce the number of objectives and enable black box verification. Here in the table, we can see that different failure categories, the corresponding design assurance level or DAL and its DO178C objectives. We can note that for DAL D, we need to fulfill 26 objectives in order to certify the software component. Note that for the highest criticality level, like DAL A, we would need to fulfill 71 objectives. And as for the step 2, which I will cover later in the presentation again, we will be leveraging the existing standards and architectural mitigation strategies that I'll introduce later. So let's dive deeper into step 1. And this is the low criticality DAL-D machine learning workflow. For DAL-D, we can treat the software component as a black box. We might have so in that black box we might have the traditional non-machine learning source code, commercial off-the-shelf software object code, machine learning models, and machine learning source code all put together into an integrated object code. We don't need to know anything. We don't need to know any of this from the outside. And for DAL-D, we can just look at this as a black box. We have our high level software requirements from which we have derived the software architecture, and within this software architecture some component is this black box. Okay, we will also develop test from our high level requirements to test this black box. In summary, the origin of the source and object code does not matter, and so the black box verification according to DO178C. it will satisfy all the objectives for DALD certification. So the black box verification techniques are the things like, testing model accuracy, for example, something we are already used to as AI practitioners. Here is just this is just an excerpt of the compliance analysis that you have to do according to DO 178C. So we can see here the objectives for DO 178C compliance analysis is shown, and for DALD we can actually omit the objectives 4 and 5. So that says low level requirements are developed and derived low level requirements are defined and provided to the system processes, including the safety assessment. So these are not applicable for DALD. And for we will be following a workflow. It's called W-shaped development workflow for developing DALD components. Okay. The W-shaped development process is this framework done by EASA to adapt the classical V-shaped cycle to AI application, and I will be adopting this workflow throughout the presentation for explaining you how can you make how can you make your AI enabled system suitable for DALD certification. Okay, as you can see, this process starts with the requirement allocation to the machine learning component, and it moves to the data management all the way down to the model training. Then we have a key step regarding the verification of the ML model and learning process, and then move to the implementation, integration, testing within the larger system under design. Note that this W-shaped development process is concurrent and it can coexist with the V-shaped cycle we typically see for non-machine learning components. So for the example, from the system or subsystem requirements, we will derive or allocate requirements to the AI component and follow the W-shaped diagram. Or if it's a non-ML item, we can follow the traditional V cycle. As we are running short of time, I will not be running the relevant models and code in MATLAB related to our case study, but we are, as Cecily mentioned, we are delighted to conduct private sessions explaining the complete demo. If you are interested, please feel free to reach out to us for the same. All right, let's move on to our case study. So in upcoming slides, I'll be showcasing you how MathWorks tools enable certification of DALD AI enabled system. And for that case study, I'll be guiding you through the various activities that must be completed in order to certify the system with an AI component. Okay. Before moving to the case study, we will need to consider certain things. Unlike the traditional software, AI software component is a solution of an optimization problem, and it is data driven. This optimization problem consists of an objective function of which we wish to minimize a complex mathematical model. Therefore, to verify the resulting AI model, specific activities are required which are not present in conventional verification and validation activities. The MathWorks ecosystem supports these activities, and as we will show, it enables a workflow that achieves DO compliance. This workflow is encapsulated in this W diagram. Okay, as mentioned earlier, traditional software and hardware verification activities follow the purple V-shaped diagram. This purple one V-shaped diagram, and pertain to non-ML related items. For DALD, the criticality level that we will that will be the focus of this section. Verification activities for the ML component are testing model's accuracy on a held out test set. Provided the model attains sufficiently high performance on a held out test set, we can be somewhat confident in the model's generalization to the task at hand and correctness of its functionality. Let's take a deeper look into the case study. So as mentioned, it's about a runway sign classifier. So before I explain further about this particular project, let's understand different types of what is a runway sign classifier and what are the different variants available for that. So the runway sign classifier, it's a system. That system is intended for detection and classification of airport signs. The system receives visual images from a forward-facing camera installed on the aircraft, and it uses a deep neural network for detection and classification tasks. There are different variants of such a system depending on the level of automation and corresponding criticality levels. So the first variant is an RSC flight back. RSC stands for runway sign classifier, and FB flight bag is being represented with FB, okay, RSCFB. This variant serves as a pilot assistance system by providing information about the detected runway signs to pilots, for example, via an enhanced vision system. So failures of such a system will have minor safety effects as the pilot is still responsible for the continuous perception of the visual environment and retains full control of the aircraft. So consequently, RSCFB can be assigned the lowest design assurance level, DALD. And there is another variant, it's called RSCSM, the safety monitor part. Okay, this system variant provides information about detected airport signs to enable cockpit annunciation or automatic braking in hazardous taxiing situations, such as crossing a holding position sign without the controller's approval. This capability provides a higher autonomy and criticality level that can be assigned to such a system is DAL-C. Okay. Now there is one more variant like runway sign classifier with full autonomy. Okay. This RSC variant is intended to support fully autonomous taxiing. In this context, the location and sign data directly contribute to the decision-making system responsible for autonomous aircraft control and preventing runway incursions. Given the potential safety impact, this kind of system, the RSC AU system, should be assigned DAL B or DAL A depending on the aircraft category. And for this case study, like DAL D case study, we consider RSC FB systems. So as shown in the image, this system consists of a front mounted camera on an aircraft, and the camera relays images, and we do some pre-processing and rescaling, and then we pass it to a deep neural network. And in the context of this example, we are using YOLO networks, and the role of these YOLO networks is to locate and classify airport signs on the runway. And these signs will be either informational signs, which appears with an yellow background, and mandatory signs, which comes with the red color. The bounding boxes and classification labels will be identified and then passed to the pilot for information and the decision-making process. So the whole system is of low criticality, DALD, and it's just providing information to the pilot, and it is not taking control of the aircraft in any way. Okay. Note that this case study is comprised of few elements, including the complete system, including everything from camera to the HUD, the ML component, and also the ML component, which is a deep neural network, and the data. For the data set, we will be using instances of different airport runways in various locations and operating conditions such as snow, weather, or like a daytime or nighttime, and with the goal to adequately represent the operational design domain. The images for the data set, it has been created synthetically using Simulink aerospace block set and flight gear. To support the discussion, for this case study, we will make reference to the system, the component, and data in the following slides. And as you can see on the slides, the example that I'm showing today is included as a part of deep learning toolbox and video qualification kit products from Artworks. The deep learning toolbox example is a lighter version of the end-to-end workflow workload example, whereas the DO qualification kit example address specific activities that support the certification against DO 178C. You can access these examples if you have the deep learning or the DO certification kit toolboxes. So for the example I just introduced, I would like to take you through all the steps in this workflow, starting with the top left, the requirements allocated to the AI component. So we have written a set of requirements in the requirement toolbox for this problem. The requirement toolbox allows you to define system requirements and then allocate them to the AI constituent. We can see here we have a system functional requirement and system operational requirement. So these are the system requirements that are derived in the system process ARP 4754A, and we will need to allocate these to the component or to the system. So we have functional requirements. So what does my system have to do? And also we have the operational requirements, in which context my system has to perform. So here we have like written a set of system requirements that we anticipate you would require for such a system. So you can see the details here. And then by using the requirements editor, we take our system requirements, for example, the weather condition requirement, and we can link this directly to our data requirements. So here we have our four weather conditions: fog, snow, rain, fair, and we can link these requirements to four separate requirements on the data. So in order to really tie these requirements to the data images themselves, we have created a data trace table. This table is automatically generated from a MATLAB script. It puts together all the data requirements IDs with the corresponding synthetically generated data. When generating the synthetic data, there is metadata upon constructions with the requirements that are met for each of the generated images. So for example, let's say I create an image in San Francisco airport with fair weather condition, and those data requirements IDs will be tagged in this metadata. And then for each requirement ID, we search through the corpus of images we have generated, put in all those images that have the corresponding data requirement ID, and then create a reference to those images through the MATLAB image data store object. So taking like a fair weather condition example, we have 114 images corresponding to fair weather condition, and they are all held by reference in this image data store. This shows how we can link system requirements to data requirements all the way down to the data itself. To go to the data level, we can simply click on the Open Data Store hyperlink, and it will open the it will opens the image labeler app. So this is the means by which we can now review the correctness of the data. We want here to check that the images we have generated are correct, or in more general terms, that the images associated with the specific data requirement ID are the right ones. Coming back to the use of image labeler app, you can use it to correct the issues with the bounding boxes or the labels, such as resizing or moving the bounding boxes, deleting the boxes, or changing the labels. When doing the synthetic data generation process, we got an incorrect bounding box position, which we can correct manually by simply dragging the bounding box as we review the data set. And then we can also compare the reviewed data with the original data set and see how many boxes we have moved. We define the tolerance as a 5 pixel shift of the box. And then comes the data augmentation. So this will improve the network accuracy by randomly transforming the original training data during the training. So here we have applied a color jitter augmentation in HSV space and random scaling by 50%. Next up in the W-shaped diagram is manage, train, and verify the learning process. Moving on to the next step, here we want to build our network architecture, train it, and verify it. MathWorks has tools interactively to design your network, allowing you to be more productive. You can also interactively track the training and performance for different experiments, allowing you to select the network that best suits your matrices. And of course, you can accelerate the model training leveraging the GPUs and the cloud. So at this point, we need to come up with an architecture to start from and analyze how different variations of the network may perform. Based on the requirement for the ML component, we decided to use the YOLO family for this example. These models require us to estimate anchor boxes as a part of the hyperparameter. So what is anchor boxes? Anchor boxes are a set of predefined bounding boxes of a certain height and width, and these boxes are defined to capture the scale and aspect ratio of specific object classes you want to detect and are typically chosen based on the object sizes in your training datasets. Once we have estimated the anchor boxes, we train various YOLO networks with some standard hyperparameters. So then we train these different YOLO based object detectors. You can see some details here. So for this particular case study, we have trained YOLO V2, YOLO V3, and YOLO V4. And here is the learning process verification stage. And for the verification, given this is a DALD component, we only require an overall accuracy on these models. So we define this as a part of the system requirements and then derived the ML component requirements that the model should have an average precision per class of at least 95%. This precision recall curves that are quite typical for models and object detectors. And we can see that YOLO V4 does not meet the requirement. However, YOLO V2 and YOLO V3 meet the requirements for all the classes. And so we will be using YOLO V3 model for the implementation and ultimately for the final system. And as I have mentioned earlier, we have a unique code generation framework that allows the model to be developed in the MATLAB and Simulink to be deployed anywhere without having to rewrite the original model. Automatic code generation eliminates the coding errors and it's an enormous value driver for any organization adopting it. And finally, here comes the integration of your AI model with Simulink. So basically in the center, you can see the deep learning object detector that we trained, and now we have few different blocks. We have the data acquisition block and a visualization block that takes the role of the heads of display. And then we are just passing a bunch of images through the running inference or simulating what the output of the network should be. Next, as we move to the final stages of the W diagram, I want to go through the process of requirements verification through testing. So recall, we had all our requirements and you can see it here. Now, for each of these requirement, we have written unit test and now we want to run those unit tests. So just by clicking, so we can just right click and run this test. And now by running the test, I can see that if these requirements are met or if they are unfulfilled. After doing this, both the system level and at the component level, I can see that there is an unmet requirement. And if you recall few slides back, like we didn't have any rotation sign images. So here is this unfulfilled requirement is representing that failed test. All right, next move on to like how can you achieve DALC certification? Okay, so we have seen how to perform assurance activities for DALD system. Okay, so DALD is a low level criticality, and because of that, we are able to treat the object detector as a black box as shown in this diagram. But now, for a DALC system, it's not enough to simply treat the object detector as a black box. We need to gain a better understanding of what is going on inside the object detector, and this includes placing the requirements on the machine learning model itself and gaining understanding of the emerging properties of the neural network. So standards will not be ready until 2025, but we can hypothesize some techniques that may come relevant to verify and run machine learning models. We'll see how can we do it. So can we tackle DALC today? Okay, and we are still waiting for the standards to be released. But what can we be today? Okay, it turns out that we can also address DALC today, and I will quickly explain how. Okay, this is uh, this is possible through the use of architectural mitigation strategy through the use of dissimilar DALT components. Okay, according to ARP 4754A, if two or more dissimilar components independently implement a system function, then you can lower the design assurance level of those system components. So you can develop DALC systems using two or more dissimilar DALD components. To reduce the chance of similar errors, the two implementation must be sufficiently independent. Okay, here is an example. It is being shipped with the deep learning toolbox. Okay, so this example shows a runway sign classification system that receives images from the forward-facing camera and then detects the airport runway system. Like I have already explained this one. What is this runway sign classifier do? Okay, here in the second figure, it summarizes the system for DALC assurance level using two DALD components. So the tool DALD deep neural networks components could be, one could be like a YOLO V3 object detector that has been constructed and trained in the MATLAB framework and saved in MAT format. And the second one, okay, it can be a faster RCNN object detector that has been constructed and trained in a non-MATLAB framework and saved in a non-MATLAB format. So in this way, so these individual components are of DALD design assurance level, but as you are employing two dissimilar DALD, and then you are using a safety monitor of DALC level to monitor the results of that one. And if there is any mismatches or if the results are not matching, the safety monitor can inhibit the further operations. So hence this system achieves design assurance level C. So here is the demo. Here is an example. Okay. So of course, moving to DALC requires going back to the requirements and making modification to some of the requirements, adding new ones, and so on. Earlier, DALD entity case study was it has in we included deep learning toolbox and DO certification kit as a part of the reference workflow example, so and so things. In this case, the test harness. Let me just run the video. Okay. So in this case, the test harness simulates through the sample of test images, performing some pre-processing, and it can be a DALC component. And then it predicts the bounding boxes from both MATLAB YOLO V3 and YOLO V2 detector. And then the bounding box information is passed to the safety monitor component, which is of DALC for validation. In the context of safety monitor component, the way it works is that if the intersection over union or IOU of the best detections of the two object detectors is above the threshold, then the safety monitor accepts the detection with the highest score. The detection box and the class label is overlaid on the image and shown in the image viewer window. The As we can see from the result, in this case, both DALD components seem to have agreed under all examples, and IOU is above the threshold for all image instances. So what are the key takeaways for AI certification in airborne systems? Okay, so there is a need to incorporate AI in safety critical situations or applications, and AI standards are still in progress. However, we have shown through a reference workflow, a case study, how this can be done today for low criticality applications. Some methods are already established and others are in progress, and we will need to wait to see how they get adopted and to what extent these methods become a part of future standards. Nevertheless, we have seen how to address DALC today through architectural mitigation strategies. I strongly encourage you to look into this end-to-end reference workflow examples in Deep Learning Toolbox and DO Qualification Kit, and this can be used as a template for other projects beyond aerospace. Now, let's start the transformation with the right support. MathWorks Pro can help you in starting your transformation journey with the AI-enabled systems, with the trials and evaluation, consulting services, training services, and technical support. And here at CES, we are delighted to serve you all the customers from Middle East for the same. And as a starting point, you can check out the AI and certification related solutions from MathWorks from the MathWorks website. And these are the two references on which these are like DALC certification and DALD certification has been explained. Thank you, everyone.